So if you have something like, let's say you have probability, this is probability of Z greater than, let's say, 2.75, right? This means that when you're doing it, the okay. This means that when you're doing it, you have, here's your curve, 2.75 is here. This just means that this boundary line is not included. But
Gotcha.
it doesn't change the region. So this becomes, this is equal to normal CDF 2.75, assuming that's a Z, which I gave you, 2.75 E99. Oops. E99, 0 and 1.
Gotcha.
And then if I had the probability, of Z greater than or equal to, it makes a difference in terms of the wording of the problem, obviously, but not in terms of the calculation. This is
Okay.
2.75, still the same. This is
Gotcha.
equal to, anything else?
Yeah. So another question. So I did this like the 6.2, like without looking at my homework, I was able to do like,
Good. Good for you.
but once I got to the 6.3,
Uh-huh.
kind of forgot like well, once I looked at the formula I remembered, but how can I distinguish when I'm looking at a 6.2 and a 6.3 problem? Like
Okay.
would it be just like looking that it's giving me a random sample and then I know to use the
That's a big part of it. So this is something that I went over, but it bears repeating. When you're dealing with the distinction here is one individual or one object, because it could be like a microwave or something. One individual, one object versus a sample of n objects or people. Okay. So what I told the group last night is that you have this formula, and you can, if you want, you can do it this way. Z, let me show you something about, I'll come back to this in a second. If I go to this is Z is equal to X bar. This is a sample minus mu, because mu of X bar is mu, right? Over sigma divided by the square root of n, right? Now, n is my sample size, okay? So if I'm doing one individual here, you can think of n as being 1 if you want. If you're talking about one individual, what is the probability that one person's IQ, let's say, is greater than 115? This is X minus mu. Now, if I do, watch what happens here. I'm going to show you something. If I start with this, sigma over the square root of n, right? And I start with the same formula, all right? But if n is 1, then this becomes this. This becomes X minus mu over sigma. Sigma's still the same regardless. But if n is 1, then this becomes the square root of 1, which is, what's the square root of 1?
1.
1. So this formula becomes z is equal to x minus mu over sigma, which is what you're used to. That's
Gotcha.
why this is for one individual. The notation is slightly different, but if you have trouble remembering it, remember this one and just think, well, I'm only using one, so that's one person.
Gotcha.
That might be a way for you to remember it. But essentially, remember, there are some problems in 6.2 that have both of these. So one part will ask you about one person and one part will ask you about a sample or a group of 10 or 15 or 30 or whatever. Okay.
Okay, and then what was the other question was using the inverse norm.
Mm-hmm. What about it?
How do I I'm trying to look at the problem. Number
Yeah, take your
15.
time.
How do I know when to use inverse norm? Because sometimes I'm looking at, is that when it has the area? Or...
Okay, so hey Alejandra, are you here? Can you hear us?
Good morning. Yes, I could hear you. I was
All
going to
right.
take a screenshot of your last
Oh,
drawing there.
no worries. I'm gonna send you the whiteboards too, but
Okay,
sure,
perfect.
feel free
Thank
to
you.
take a screenshot. I'll go ahead and let you.
Okay, thank you.
No worries. Elizabeth was just asking some general questions. She asked about the difference between greater than versus greater than equal to with the normal CDF. There is no difference in terms of the normal CDF inputs. There is a difference in the language of the problem that we were talking about. Okay.
Okay, thank you.
Of course. And now she's asking about the difference between inverse norm versus normal CDF. And I think the best way to show that, I'm going to put it on the whiteboard too, but let me show you this because that's a really good question. And every semester, that's a question that a lot of people have, but let me show you. And it's not, I don't want to call it easy, but it's straightforward to sort of figure it out. What I like to do is show people the inputs of this. So if you have, let me make sure I'm sharing the screen here so you can see. Can you see? Not yet. Can you see my calculator on the screen?
Yes.
Yes.
Okay, so now let me show you this. So if you look, I'm going to go to second distribution. Okay, both of these commands are on the normal distribution menu. If I go to number 2, which for me is the normal CDF, right? Notice what they're asking for. Okay, notice what they're asking me for. Lower, upper, mean, and standard deviation, right? And what comes out of here is an area. So if we continue with the example that we've been using, 2.75, because that was the z-score that I just gave you on the last problem. That was arbitrary, didn't come from anywhere. That was just a z-score that I made up out of my head for the sake of this problem. Let's say we're going to infinity. Remember that second E99, 0 and 1. What comes out of normal CDF is an area or a probability, depending on the context, okay? So what comes out of normal CDF is an area. If I were to say, so this is what I wanted to make the point, and I'll come back to that in a minute. But when I have, whoops, when I have normal CDF, normal CDF inputs are Z or X value. Sometimes P hats, right? But they come from Z or X usually, right? So, and the output of this is an area. So output is area or probability, right? That's normal CDF. If I'm doing, so if I just draw this again here, this is the same picture that we just had, but I'm redrawing it for clarity here. This is 2.75, 2.75, right? So my area here, assuming that I'm doing this, is that. And let's say this is our Z-score, right? So what comes out of this is normal CDF 2.75 E99 0 and 1 because there's these, okay? And what I got from it was, hold on, let me go back to the calculator. What I got out of it was 0.00297, 0.0030. So this is equal to 0.0030. Now, why do I bring that up? Because if I say something like this, if I say something like, let's do this in context. If I were to say, okay, here's a distribution, and I were to give you this. Now watch, instead of giving you this Z, and I'll make it easy, I'll make it a Z-score that we want rather than an X, so we don't have an extra step. If I were to give you this, 0.0030, okay? If I were to give you that, that's an area under the curve, right? That's not a Z. So I can't use normal CDF for that. I use inverse norm, which is INV norm, when area is given and you need an X or Z or P hat. Okay, so common person. Now, why did I say looking at the inputs would help you? Because if you look at inverse norm, look at what you have. Inverse norm, if you go to the calculator, and we will in just a minute, what you'll see is it's going to ask you for area. It's going to ask you for the mean and the standard deviation, right? Just like before. Now, if it's asking me for an area, see, it's asking me for an area. So the output of this is not going to be another area. because area is an input in here. What comes out of this is some sort of, what comes out of here is some sort of score, some sort of X or Z or P hat. So that's how you distinguish it, okay? Now, how does it look? Let me show you here, and then I'll go back and point out something else. If I go to second distribution here, and I go to inverse norm on this screen, this is number 3 now, it's asking me for an area. So the output of this, let's say I give it I'm gonna give it 0.997 because I gave it 0.003. 997. And I should get something close to, yeah, 2.75. Now, why did I give it 0.997? Because remember, when we're using inverse norm, the calculator wants this part. Calculator wants this. Calculator wants the left area. And that's just a limitation in the programming of the calculator. Now, some of you might have left, center, right, and can specify, but for the sake of the instructions here, we're assuming that your default is to the left. So the thing I wanted to point out, let me bring up something else here so I can show you. So I can answer this more fully. Downloads. Let's try this. Is this my slide? I don't want PowerPoint. I want the homework. 6.3. Hold on. Hold on. I want homework. Okay. No, that's not what I wanted. Let me go to PowerPoint up here. Because it's not giving me what I want. So let me open it. Bear with me for just a moment here. Open. Okay, we'll do this. If I'm looking at okay, take a look at this. I'm going to share the screen here. Let's look at this again. A hardware store receives a shipment of bolts that are supposed to be 12 centimeters long. So they're supposed to be that long. The mean is indeed 12 centimeters, and the standard deviation is 0.2. For quality control, the hardware store chooses 100 bolts at random to measure. They will call the shipment defective and return it to the manufacturer if the length of the 100 bolts is less than 11.97 centimeters or greater than 12.04 centimeters. Find the probability that the shipment will be found satisfactory. Well, here's what this looks like, okay? Let me show you the picture before we go to the calculations, because I think the picture is more explanatory. We have a picture here. Mean here is 12, so you've got 12 in the middle of that. And you're looking for a z-score for each of these, which she calculated. See, 11.97 is over here. So she did 11.97 minus 12.02, negative 1.5, and positive 2. And so satisfactory is going to be in here, in this red region. Notice here, this is normal CDF. Why? Because we're looking for the probability between the numbers. Now, if I have this, compare that to this example. Suppose that a particular professor's statistics exam on probability traditionally has a mean score of 74 with a standard deviation of 11. The professor suspects that his current crop of students is very strong. To compare, he gives them the same exam he has in the past. The sample mean of the 28 students was 78.3. Was the professor correct? So here's what's going on here. This is the difference. So in this case, and we'll go back to the solution in a minute, but here, the mean is 74, right? Mean is 74. Now, they're over here at 78. Okay. 0.3. Again, if they're scoring higher, that's going to be an X bar, right? They're scoring right here. What's the probability that they fall right here? How many, right? But if I ask you this question, if I say what percentage or what is the probability? What percentage of students fall in the, say, 90th percentile for this distribution, right? Your mean here, just for mean, is 74, and your standard deviation is 11. Well, now, mind you, I'm extending the problem here, but I'm doing it for a reason. So let me get rid of, whoops. Didn't want to get rid of that. Wanted to get rid of this line. So let me get rid of that line. And let me do this. So I'm looking at this point here, 90, right there. This percentage is 90 percentile, right? Now, that means that 90% of the students are below me. That's this whole, don't think it's just the left side, it's the whole piece. This whole portion here. Okay, so this whole thing is 90. So what is this tail piece? Everybody's muted. Can you hear me?
Yeah. What's the tail piece? Would it be 0.5? 0.05?
Not 0.05, because this whole thing is 90, right? This whole thing is 90, all the way from the left all the way up here. So this tail piece is not 0.05, it's 0.10 or 0.1, right?
Mhm.
So this is 0.1. This is an instance where you would
You minus?
find You would
One
find the inverse. Yeah, you would subtract it because that's how I got this. So the area, remember she's been right. If you've been in class, you've seen this. You'll see her write stuff like the area to the left plus the right tail equals 1, right? Or she'll write area 1 plus area 2. This is, sometimes she writes this. Sometimes you'll see her write like area 1. And this whole area is area 1. So this whole area there. And then this whole area is area 2, right? This tiny piece here. Area 1 plus area 2. And remember, area 2 is 0.1. So if that, and that's equal to 1. So you'll see her write area 1. And it doesn't have to be in a particular place, but she'll divide the distribution into 2 areas. Area 1 plus area 2 is equal to 1 because that's 100%. So area 1 we know is 90% because it's the 90th percentile, 0.90, right? Plus area 2 we have, which is we don't, let's say we don't have that. Let's say we're going to solve for that. So this is going to be, we know that it's 0.1 because we did the math. But if you want to do it like an equation, area 1 was the only thing that was given to you. This is where it came from. And that's where your subtraction comes in. Because you're doing 1 minus, so area sub 2 here, area sub 2 is equal to 1 minus 0.90, which is 0.1. And that's this area here. Now I need to know I need to know area 1 for this. So if I say, when I do it, I want to know what that score is, right? Well, if I put in the z is going to equal inverse norm. Remember, area to my left, which is 0.90. 0 and 1. So if you put that in your calculator, tell me what you get when you do that. I'll do it too. So we're gonna do second. I'm gonna do my little trick here. Inverse norm, and I'm gonna go change this input to 0.90. So this is this, and then I'm gonna come over here. And that's gonna give me 1.28. Is that what everybody got?
I didn't put it in my calculator.
So inverse norm is 0.90. Now this is my z. Now I have to go find my x. Right? Because I asked you for the score. So if I take this and say, all right, I asked you for what is the score. So at this point,
Shauna, I'm sorry. What was it 1.28?
1.28.
Okay. And we stopped there, second decimal.
For the ZZ, if you take it to
Okay.
4, she's not going to dock you, but Z scores normally go
Okay.
to 2. Now I said, what percentage of students fall in the 90th percentile? Well, 90% of them. What I should have asked you was what score This is a better question. What score separates the top 90% or the top 10%, the top 10% from the rest, right? So the top 10%, top scorers are going to be over here on the right. So the top 10% from the rest of them. Well, we know that's a z-score of 1.28, but what's the score? Well, it's 1.28 is equal to, now, using our little trick, even if you don't know if you should divide by, and I forgot to give you a piece of information up here, n was 28, right? We had that in our example. So if you're not sure, well, n is 28, so you have to be dividing by the sample size this time. So you're going to get x bar, which is, in this case, I'm going to use 74. I think it was 78.3, but I'm going to use 74 because that was your new group. Okay, this was x bar. This was your x bar, and x bar was 78.3. I didn't give you that either. I gave it to you, but not, I gave it to you on the other screen. X bar is 78.3. Mean is 74. Your sigma is 11. And your n is the square root of 28. So you divide that out. Now, if I'm looking for, this would have been my situation if everything was given to me, right? But I don't know what this x is. I don't know what, see, that's the thing. I don't know what this x actually is. So, because I don't know what this is. So this is not 78.3 anymore because I don't know what this x is. That's the new mean over here. So actually, this is going to be x. So I have, this is x minus 74, because remember, that's my mean. So for x, so multiply 1.28 by 11 to clear the fraction, and then, or 11 divided by the square root of 28. This is divided by the square root of 28, because remember, we have 28 people. So then you'd solve. But my point in doing that is not to, it's not to confuse you. It's to remind you that when you're looking for an inverse, you can do this with this problem, or you can do this with the one where you're doing it for an individual score. We don't know what this x is. In part A, when we were over here, we did, because we were looking for this portion. We knew what that, see, that mean was, that sample was 78.3, but we don't know now because we're not at the mean anymore. We're here, right? We don't know where the 90, so I would have to calculate this and then do some algebra to manipulate it. But the difference between normal CDF and inverse norm is in what you're given. Okay, whether you're doing one value or many. Okay, anything else?
And then just to confirm, she said we can use I think she said in class that we can have like a index card with like to guide ourselves, something like
The
that.
formulas for 6.3.1 that are not on your formula sheet is what she said. Because the
Which one?
the formulas for the distribution of sample proportions, the homework assignment that wasn't in your book, you can add those formulas to an index card and put them on your formula sheet.
6.31.
6.31. So the assumptions and the formula for p hat, I think the formula for p hat is already there on your formula sheet, but you can have that. And then that's what she said. But there's not that many formulas for 631 that you don't have on your formula sheet. The others should be there already.
Okay, thank you.
Any questions, Alejandra?
I wanted to review homework 7.2 if you have time.
Sure, I can look at that.
Okay.
What's going on with 7 point?
I mean, I realized that there was an attachment. It's called confidence coefficient for the t-test. I know at 7.1, we were finding.
Sorry,
It
China,
looks-
I'm gonna have to log off.
Sure, Elizabeth. I'll see you in class.
Okay, for sure. And then today's quiz gonna be on the 6 point
It's gonna
6.2.
cover 6.1 to 7.2.
Oh, then, okay.
But your in-class portion, I think, only covers 6.1, 6.2, 6.3. I don't
Okay,
think
gotcha.
it covers chapter 7 in class, but you do have an additional. I will be pushing out a meeting for some time tonight, but I think tonight I have to leave by 8, so I'll probably start the meeting around 7 o'clock, maybe 6:30.
That's perfect.
But there will be a meeting tonight, so I just haven't had a chance to. But the tutoring session from last night is up. It went up this morning. This will go up after I come back because I won't have time to upload it before I have to leave. But
you, guys.
there is probably, I have to look to see, but I'm sure there's a video up for 7 too. I mean, it's been up, but it's just a matter of finding it.
Oh, really?
So
Okay, I didn't
yeah,
find it.
it's just a matter of finding it. If it's not up there, I haven't been able to, because I've been running around like a chicken with my head cut off. But I will look for that and I will push that out to everybody.
Okay. Yeah.
But yeah,
I think I went through all the videos, fast forwarding,
Oh,
see if I would find it.
maybe I.
Okay.
And honestly, in your defense, Alejandra, I honestly thought it was up like 6 months ago from that class, and for some
I
reason it
see.
never got uploaded,
Oh, no worries. It's
which is
okay.
why it got uploaded this week, because I'm like, uh-oh. I'll check and see, but yeah, we can
Okay,
go over
thank
that.
you.
What is your question
Okay.
about
So
7.2?
finding
See you, Elizabeth.
the t-test, it looks like, for t-test. So I noticed it looks similar. I think it's 7.2 problem number 2. I think if I do one, I could do the rest on my own. So I have like T.
Yeah, let me do something. We have about 30 minutes or so we have
Okay,
some
thank you.
time. But let me just do a couple of things, because
No
yeah,
worries.
I know that that's an issue, is the You're in the online class, right?
Yes, online.
You have a tiny bit more time than the other class, so I'm not as let me just look for something here.
Okay, thank you.
So I can. Yeah, you guys are good for me because you guys keep me on my toes all the time. 7.2. Let me check something. Because I'm pretty sure that okay, that didn't give me anything because it doesn't recognize it. Understandable. Why not? Hold on, let me go to my mail. Oh, okay, my internet connection was. Don't do this to me right now, internet. Let me see. It doesn't want to load right now, but I'm gonna make it load. Just a minute. Let's see. Settings. Okay, let's see. Yeah, my internet is being a little spotty at the moment. Let me connect and see if this helps at all. Does it? All right, let me try something here. It doesn't want to load my email, but let's see. Let's see if it'll load right now. There it goes. Okay. All right. Let's see. Central. No, this is confidence interval. Well, if you spell it correctly, confidence interval. 7. Here it is. Okay. I'm going to forward you something here. So there's finding each of the t's, right? There's finding t values, which are similar to finding, they're similar to finding z's. What I'm gonna do here is I'm going to forward this to you. Here. But occasionally it happens. So this is a problem from 7.2. In 7.2, we're finding confidence intervals for means, but we have we're learning about a new distribution, and that requires our testing our assumptions, because we referenced this yesterday, and remember I was like, where are the T's? Because I remembered there were T's, and then I didn't remember they didn't come up till 7.2. That's why I couldn't find them
Okay.
the other
Makes
night.
sense.
But remember, I was telling you and Jay, I'm like, I know there's T's. I know there's T's. Where are the T's? When you, and this is going to come up in hypothesis testing in chapter 8 as well, but we don't have 8 on this quiz, so don't worry. When you find confidence intervals for means, okay, you have to choose the correct distribution, okay? You have to choose the correct distribution. We have Z or T. We have 2 of them, okay? We are very familiar with the Z's. T's are new for us in this section. So basically, you're going to ask yourself 2 questions. You ask 2 questions, okay? And this is on the slide. If I have time to find the slide, I'll go over it. But there's a flow chart in 7.2. You ask 2 questions. You ask, is sigma known? Remember here, and this gets to be very important too. There's 2 standard deviations. There's a sample standard deviation and a population standard deviation. Sigma, that little circle with a line over it, sigma is the population standard deviation, okay? So is the population standard deviation known? And the second one is n greater than or equal to 30, okay? This is your sample size. Now, you can have 4 possibilities, 2 yes, 2 no, or yes, no, depending on whether you get yes to the first one and no to the second one. Now, let me go down here and let me stop sharing because I need to show you one thing before we continue, which is not that. I need to show you the PowerPoints for 7.2. So let me scroll down to, here it is. Okay. This is our thing. If you look here, talks to you about T's, talks to you about, now here's your flow chart, slide 8 right here. You have to show that you answer these questions. Is sigma known? If sigma is known, you use a Z, just like 7.1, regardless of how big the sample size is. So if you know the population standard deviation, you use a Z, period, you're done. Okay. If sigma is not known, and by the way, you answer both of these questions, regardless of what the answer to this first question is, you answer both. Is sigma known? If it is n greater than equal to 30? If it's not, you uses T and you use S, which is the sample standard deviation. That's why you need to know the difference. Okay. In place of sigma. And you use, if it is, then you use Z of alpha and you use S. So this is your flow chart. This is your golden ticket right here, okay?
Okay.
If you get 2 no's, I don't know sigma, and N is smaller than 30, that's my destination to the T-score. Okay? That's my destination to the T. If you get 2 no
Okay.
answers, that's the
Mhm.
T.
Okay.
Now, the T has a little bit of a nuance. It's very similar to the way the Z works, except that, and I'm going to show you this on the example that we're doing. Let's
Is
say
that the
that I give you,
DF?
yeah, you have a degree of freedom, exactly.
Mhm.
So here, let's say we have this problem here. The predicted high temperatures for day in late May for a random sample of US cities are listed here. Estimate the mean population high temperature with 90% confidence, okay? Estimate the mean. So that's another way of saying find the confidence interval, right? Because we're estimating the mean. Now we're estimating the mean, so we have to decide, is this a Z or a T-score, right? Now, how did she get, this is the other thing. How did she get X bar, S, and N? Well, she has these raw data. So you put the raw data in the calculator. So 60, this is something that we did before. 60, 88, 73, 86.
This is the O1.
103, 79. You have to put them in the calculator. 63 or 67, sorry. 88, 76, and 87. So what I'm going to do now is I'm going to go, this is what we have to do. We have to go to the calculator here. Anytime you have raw data, you have to go to the calculator. So I'm going to go to the calculator. I'm going to go to Strat. I'm going to go to Edit. I'm going to have to clear my list. So I'm going to go to Clear, Enter, and I'm going to go Clear, Enter here. I only need one list for this. Make sure that when you clear it, your list name is highlighted. So I'm going to enter the data values that we saw. So 60, 88, 73, 86, 103, 79, 67, 72, 89, 88, 76, and 87. And if I did them all correctly, we're going to go to Stat, we're going to go to Calc, and we're going to go to one var stat. We have it in L1, so we calculate L1. We've done this before. And what you're going to look for is you're going to look, X bar up there is your sample mean. So you're going to write that down. X bar is 80.6667. Then you're going to look for you're going to look for SX, not sigma. This was a sample of values. This wasn't everybody. So look at SX in the middle of your screen. 11 point, SX is 11.6667. 7422. 7422. And N is 12. Okay. That's where she got her numbers from. Okay. If you get different numbers, you may have made a mistake with the data. Sometimes we make mistakes with the data, but check your data first, but it should match. So we have, 80.6667, 11.7422, and N is 12. Okay. This is going to be the case if you have raw data. This is going to be the case whether you're using Z or T. You'll have to go to the calculator to do it. Now, based on the flow chart I just told you, do I know sigma? Do I know it for the entire population? No, I don't. So I don't have sigma. And is my N greater than 30? No, it's not. Since I got two no's, it's a T. The formula is right here, okay? The difference in this formula is that you have a T of alpha 2, okay? T works just
quick question. How do we know that N is not greater than, because we have the N from the calculator. Got it.
Right, but also N is, what does N represent?
Sample size.
Sample size. So in this case, when they don't give it to you in the problem, how do you figure out what the sample size is?
I could just count the
You count them. So in this case,
so it was getting
in this case, N represents the number of data values you have. So sometimes they tell you how many, sometimes they don't tell you how many, but that's a good question. So if you have data values, the size of your sample is how many data values you have. Okay. If you have data values, the size of your sample is how many data values you have, which are 12 here. Here's my formula. You'll notice it looks very similar to the Z formula, okay? Except that there's S up here. Remember, S is the standard deviation as well, but it's the standard deviation of the sample, which is why we needed to get it from the calculator. It's right here. And this T of alpha, this is what's new for us, okay? We were getting Z's in 7.1, okay? The way we get T's is very similar. You don't use inverse norm, you use inverse T as in Tom. And it's 1 minus alpha over 2, but we have this extra thing, which is the degree of freedom, okay? Without getting into too much detail, the degree of freedom for a T-score, the degree of freedom is always 1 less than N. So in this case,
11.
Yes, the degree of freedom is always, by definition, and you can see this in the slide, the degree of freedom here, degree of freedom is, is N minus 1. So that's always whatever number of data values you have minus 1 from that. So that's 12 minus 1, which is 11. You put it in your calculator. So we're asked to find it with 90% confidence. So let me go over that for you. Because that's the new piece. The other pieces should be fairly similar. So here, if you remember, whether we're doing a Z or a T, we're going to say that we have our distribution. You do not have to draw this, but I'm drawing it so you can understand what you're doing here.
Thank you.
For 90% confidence. So remember, that represents the stuff in the middle that we're confident of. This is 90%, okay, in the middle of this, 90, right? We're looking for these boundaries here. Now, my T, because when I'm doing confidence intervals, I want the positive because the T's are symmetric, just like the Z's are. They're a little bit broader and a little fatter at the ends, but they're just like Z's in that respect. So I'm looking for this T, right? Turns out I have an inverse just like I do on the Z. And since I'm looking for this T-score, I'm going to say that T of alpha 2, because remember, that's the notation that's associated with your confidence interval. T of alpha 2, T of the tail area is equal to, and this is going to be, and you're going to have one of the T's, because we're only concerned with the positive one here, just because that's what we're going to be writing. But you're going to end up with a positive and a negative. So this is inverse T. Remember that. If you're consistently getting these wrong, and you're off by a little bit, and you cannot figure out why, one of two things is probably happening. Either you're trying to use a Z distribution, a zebra distribution, when a tiger applies, or you've substituted these values, because these are not, like if I give you the Z score for 90, that's 1.64, right? And what I see students do sometimes, especially if they're doing the two sections together, is they'll import the Z value from that into a T distribution. Very common. Be careful of that, okay? So before you chalk up the whole problem and do it again and throw it away, check that. That would be the first place I would check something.
Okay.
Especially if it's a mistake and you can't find it. I mean, it could be other things, but that's the first line of defense is to check that. So inverse T, this is going to be 1 minus alpha over 2. And this has a DF. So we're going to, this also has a mean and a standard deviation. We don't worry about that. You only need
0.01.
these parts for this one. So now remember too that just like in the last section, your confidence level is 90%, 0.90, okay? Your alpha is always 1 minus the confidence level. No matter what distribution you're on, alpha is 1 minus the confidence level. So in this case, this is going to be
1 minus 1.645 or no?
So inverse T of 1 minus 0.90 divided by 2. I'm sorry, 0.10. 0.10 divided by 2. It's not 1.645 because it's not a Z. Okay, I'll do it right now. Alpha is equal to, this is 1 minus, remember this step you need to do so you know what the alpha is. This is 0.10. Okay, 0.90. This is 0.10. Okay. So this is 1 minus 0.10 divided by 2. And your, oops, let me erase that. And your degree of freedom. So this is 1 minus 0.10 divided by 2. Remember, we have 11. So when I go to do this, I get the following. Let me switch screens. I have second quit. So it's second. It's on the distribution menu, just like the last one. Inverse T. Notice it doesn't ask you for a mean and a standard deviation here. Your area is 1 minus your 0.10, your alpha
Right.
divided by 2.
And in the
This-
DF, we put that separate.
This is 11. You paste it. So if you don't have the ones where it asks you, your input is going to be after that. So 1 minus 0.10 divided by 2, comma, and 11. Inverse T should give you 1.79588. So 1.796 or 1.7959. If you take it to 4, 1.7959. 7959. So here, let's see where she took hers. I think she takes her T's to 3 normally, but let's see. This is your, yeah, so she got 1.7959. There was my T value, right? And now from there, it's just like, whoops, it's just like before. It's just like before. You go ahead and
Find the parenthesis first.
yeah, you
S.
find
Okay.
the hold on, let me come over here because it doesn't want to show me, so I'm going to make it, that's whiteboard. I don't want whiteboards. I want the, give me a minute because it went away. And let me share the screen here. That's not the one I wanted. That's the one I wanted right there. No, that's not. I downloaded the wrong one. Lovely. All right, let me, bear with me for a moment here. Let's see. So this is gonna be, you're gonna do the same thing we did last night. So you're gonna take, where is the email at that I have? No, that's not it. I can't find the email. Okay, well.
Is it the one that you just sent me?
Yeah, but I want to bring up the screen so I can show you. I don't have time to do the whole
No, it's
calculation.
okay. Yes.
But I want to
Okay.
put it on the screen for the sake of the people who are watching it.
Okay.
So but it's, you're gonna do the same calculation. Where is it there? I'll have to bring it up again because I don't know where it went. Lucky me. All right, so now I think it booted me out is what happened. Let me go to my items here and let me look at problem. Which problem was it that we were doing? This one, I'm going to download that. So I can, there we go. Alrighty. Sorry for that station break, folks. Technical difficulties. We are here now. So we have calculated the t, which is right here. And now here's the formula. So my suggestion is that you calculate the error as we discussed. Calculate this first. Remember, this S came from the calculator, 11.7422 divided by the square root. Be careful here also. This is another place to make an error. This element of the formula, this is N. This is not your DF, okay? DF is in your alpha here when you find your T.
Mm-hmm.
One less than N. When you divide in the confidence interval, you're dividing by the sample size. So be careful. If you get a wrong answer, that's another place to check. Make sure that you're using inverse T and not inverse norm. Okay. Make sure that this is DF, which is 1 less than N, not N. Okay. This is N minus 1. That will throw you off. And make sure that you're dividing here by N, not DF, okay? That's another thing that happens. Go ahead and calculate that, and she did that separately. You can see that here. Margin of error is equal to E, which is 1.79. This is her error term right here, okay? So she's subtracting the error here and adding the error over here to get her final answer, which is right here. Okay, that's how this works. Okay, any questions about that?
No, thank you so much.
You're very welcome. Thank you for coming. Thank you all for watching this video. Let me know if it was helpful to you, hopefully. And I will hopefully get it posted sometime soon today. So you'll have some time to work on the take-home portion of this, and it will be up there. But the other tutoring session is up already. And there
Okay,
hopefully will be another one tonight. I'll push that out as soon as I can.
Okay, perfect. If not, I'll see you tomorrow morning, 10:15.
Oh yeah, we'll be around. We'll be
See you
back
then.
again.
Thank you. Yes,
Take
thank you.
care.
Have a good day.
You too. Bye now.
Bye.